Right. Good evening, everyone. For our last talk of the day, we will have Fun with Plastics by Professor Richard Kaner. Professor Kaner is a distinguished professor in the chemistry and biochemistry department and the materials science and engineering department. He has received awards from the Fulbright, Guggenheim, and Dreyfus Foundations and the American Chemical Society. Furthermore, Professor Kaner has been at UCLA for over 30 years and is among the most highly cited researchers in the world. The Kaner Lab studies super hard materials, battery technology, and conducting polymers with applications to clean energy and water purification. A round of applause, please.
Oh, microphone. Oh, very good. So today we're going to have some fun with polymers. So I'm going to start with this. What is this? A balloon. What's a balloon made out of? Rubber. That sounds good. Where does rubber come from? Rubber tree. A rubber tree. Sure. Yeah, it does. And here I've got liquid nitrogen. Okay, where does nitrogen come from? The air. Yeah, the air is about 80% nitrogen and not as much oxygen. What do you think will happen if I put this balloon in liquid nitrogen? It'll freeze. Okay. Well, let's watch what happens. I'm trying to hold this in the liquid nitrogen because it doesn't really like it. It'll break. Shrink. Yes, that's exactly what it's doing. It's shrinking. Okay, and I should be able to shrink this pretty small. Why is it shrinking? Anybody know? Liquid nitrogen's cold, and what's inside the balloon? Air. And what's the air made out of? Molecules. And the molecules, so here we go. Here's a cold balloon. You can touch it, right? Yeah, sure, you can touch it. It's very cold. And what do you think is going to happen as it warms up? Yeah, go ahead. You want to see what's going to happen? Here, throw it. Just throw it around. It's reinflating. Yeah, so basically, the air is about 80% nitrogen. Most of the rest is oxygen. And when we put it in liquid nitrogen, it basically compresses the air into a liquid, which takes up much less room than the solid. And when it warms up, it just simply reinflates. So there's all sorts of different polymers. Does everybody have a handout? Did we get those sheets handed out? Here, pass out some more. We're passing out sheets that have different polymers. And we're going to talk about different polymers. So first of all, anybody know what this is? What does it look like? Well, that's a good guess, a graduated cylinder. Any other guesses? Tube, yeah. What kind of tube? Yeah, good. It looks like a test tube. What if I told you this is a soda bottle? It's a 2-liter soda bottle. Yeah. Yeah. No, you couldn't drink soda from that. So what you have to do is you have to heat this up and then you injection mold it. They put hot air in and they blow it into a mold. And when they're done, this is what it looks like. Yeah. It is pretty cool, isn't it? So, yeah. So I'll pass this around. Now, if I look at this, you know whose Coke bottle this is? Well, I don't know. I'm looking at the Coke bottle and Pete's name is on it. That's what I want to know. Who's Pete? Does anybody have on their sheet, you have a list of polymers. Can anybody figure out who Pete is? What number? Go ahead. 1. What is what? Can anybody name what Pete is? It's under 1. Poly? That's good. Polyethylene terephthalate. Okay. Or also known as PETE or PETE. That's number 1. They're the most recyclable of all polymers. Why? It's also fairly expensive, but you can remelt this and remake this. So pass this around. Go ahead, pass that around and pass this thing that looks like a test tube that we can turn into that. Okay. So you heat up polymers, you can melt them. And polymers generally have the following structure. Do we have a marker? one that works, preferably. All right. So this is, as a chemist, this is how we draw polymers. And that would be polyethylene, and these are carbons. And there would be 4 bonds, so these would be hydrogens coming off. But we just make this swiggle. And almost all these polymers are like that. Does anybody know what number 2 is? HDPE. What does that stand for? Good. High density polyethylene. Okay, we're going to see what that's like. If you look at this object, does anybody know what this object is? It could be a cup. We could pull the top off and we could drink out of it, so it could be a cup. It is a jar. Now, let's see who can read the top. Read what it says on the top. Betty Crocker. Good. Okay, it says Betty Crocker on the top. Now who knows what was in this jar? Frosting. This is, if you ever frost a cake and you don't want to go to the trouble of making your own frosting, you can go buy a jar of frosting. That's what this is. But what I'm interested in is what's the jar made out of. So hey, that's good. You read minds. I was about to ask you to read that, but you did. HDPE, which is number which? 2. And 2 is what? High density polyethylene. Now, here's a good one. Can you read the number here? It's really tiny in that triangle. Number 4. What is behind door? No, what is number 4? Low density polyethylene. So now we're going to find out the difference between low density polyethylene and high density. So the high density is hard, right? Because you want to hold the jar. And the low density is soft because you want to be able to pull the lid off. Okay? So if you're ever playing with polymers, one's high density, one's low density. How many people are good cooks here? Do we have any? Okay, good. Then I got a question for you. If you're a good cook, do you use handy wrap or saran wrap? Why? That's a good answer. It clings better. Yeah, that's exactly right. It does cling better. Because handy wrap and most, like if you store brands of wrap, is just pure polyethylene. Okay, and pure polyethylene is just that backbone. Ethylene is 2 carbons, and you just polymerize them. You get a few million units. It doesn't cling very well. But saran wrap actually has chlorine in it, and it's polydimethyl chloride. So instead of having the carbons and the hydrogen, it has some chlorine. And those chlorines add a charge, and that charge clings. So if you're willing to spend twice as much, you can get saran wrap that clings. While we're cooking, anybody know what this object is? Silicone. It is. How did you know it's silicone? Oh, that's good. It does say silicone. I didn't think anybody could read it. Yeah. Oh, thank you. You brought me back the balloon. Don't worry, I got more. Thank you. So what would you, if you're a cook, what would you cook in here? Bread. Yeah, this is actually a bread pan. Now, silicone is made out of, it's like that, but it's silicon and oxygen as the backbone. It's very flexible. If you're a really good cook or a really good bread maker, you might not want to use this. What would you use instead? Yeah, what's a bread pan usually made out of that you bake bread in? Metal. It is. It's metal. And because it's metal, it gets really hot. And because it gets really hot, your bread gets a really nice crust. Now, this is much better for if you want to take out your bread because this doesn't get very hot, and you can just pop the bread out because it's very flexible. The trouble is you don't get as good a crust. So if you're really good at making bread, you might not want to use this. However, if you like to make cupcakes, I highly recommend cupcake pans made out of silicone because your cupcakes jump out. You know, most people who make cupcakes have to put those little foil wrappers in so they can pull it out of the pan. But with a like this, you wouldn't need that if you didn't want it. Anyway, let me pass this around. You can see what a silicone bread mold looks like. Now, while we're on the subject of food, what are these? packets. What comes in these different packets? Sauces, here's one. Mustard, this one. Ketchup, soy sauce. Okay. How many of you have had trouble opening these? Like you go to open them and they end up all over? Yeah. Okay. So this is probably the most important thing you're going to learn today, how to open these packages properly. So in order to understand how to open these, we got to know what they're made out of. So anybody know what this looks like? Go ahead. It looks like aluminum foil, and that is a good guess, but we came here to talk about plastics. And so this is a plastic, but it's been metallated with aluminum. Okay, how many of you like to get helium balloons on your birthday? Yeah, everybody likes to get okay, you like to get a helium balloon, right? All right, so the problem, if you take a normal balloon like we looked at, a latex balloon like this, and you put helium in here, what happens? How long will, it does float. And how long does it float? Not long. Maybe the day of your birthday. On the other hand, if you coat this with metal so it looks like this and you get a mylar balloon, it may last a month. Okay, yeah. Why? What's the problem with helium? Well, there's a different problem. Why? Go ahead. That's right. Helium wants to rise. It's much lighter than air. And if you have helium in a latex balloon, it simply goes through, it slowly leaks out. And one day it's all leaked out. But if you metallate the polymer and you make something called mylar, then it won't leak out. You can last a month or longer. All right, so this is actually quite useful. Now, originally, it was a very expensive polymer. They made polyethylene terephthalate, number one, and they metallated it. And it took many years to figure out how to metallate polyethylene, which is much cheaper. That's what they do now. That's why these mylar balloons are not all that expensive these days. However, the same thing is true of these soy sauce packages and ketchup and mustard packages. They're made out of polyethylene. Now, when you pull polyethylene, when they're making it, it's oriented. If you're the manufacturer, would you orient it the long way or the short way? What do you think? I think you're going to do it the long way, right? Because it's coming out on big rolls. Okay, this is key. It is oriented the long way. Hence, if you get a package and there's no little thing that says to open it, which way should you open it? You should open it the long way because it will split that way very easily. The only exception is if there's a perforation on the side and it says open here, that's okay. If it says open here and there's no perforation, don't believe it. Do it the long way. And most of these packages, you'll see they're frilled on the top or bottom. That gives you a hint of which way to open it. Yeah, so you'll save yourself a lot of spills by doing that. So it helps to know what these things are made out of. Now, which polymers, how many polymers are there on that sheet? How many numbers are there?
There are
7. And if you happen to live in Los Angeles, which numbers are recyclable? Anybody know? I see 1, 2, 3, 4, 5. Keep going. You have more fingers than that? No, he's just got one hand. Can we recycle 6 or 7? So it turns out in Los Angeles, you're right that 7 is other, but in Los Angeles, you can recycle any polymer that has a number, including 7. Now, what happens with it when it gets to the recycling place is a different story. So there was a time when number 1 is the most valuable one. So they will pull out the Coke bottles. In fact, most of you pay a dime when you buy the 2-liter bottle or a smaller bottle, and you can sort of get that back if you know where to take it, but nobody knows where to take it. So we all put it in our blue bins, and those get sorted. But most of the rest of the polymers, they're not valuable enough. So a lot of it ends up in landfills, but hopefully it ends up segregated so that someday when it is valuable enough, they will separate it out. By the way, if you go to a landfill, there's people who study landfills. Do you know how they figure out how old a landfill is? Like, let's say you wanted to study what life was like 50 years ago or 100 years ago. So you go to a landfill, and you drill and you get a core sample. You know how they figure out how old it is? Yeah, so they look at it turns out that in a landfill, every day we throw things away. They go to these huge landfills and they put a layer of plastic, polyethylene on top. And then the next day they come back and they fill it up again and they put another sheet of plastic. And so all the air is sucked out. And so even things like grass and, food waste, a lot of it doesn't decompose or decomposes very slowly. So they can literally pull out newspapers and look at the dates to figure out how old it is. Yeah. So you might think that things digest. They do slowly. And in fact, UCLA ran half of we have a cogeneration plant. And for many years, they just simply went to a landfill and they stuck a pipe in, and methane, which is natural gas, as things decay, food waste and so on, it produces methane. So that methane was filtered and pumped here and was burned, and we supplied half the energy of UCLA for many, many years off of that. So there are things you can do, but a lot of plastics end up, the best thing is to recycle them, because if you throw them away, they don't degrade. In fact, one of the interesting things is people worry about if you eat a polymer, is that bad for you? Well, as long as you don't choke on it. So a normal thing that you eat are called monomers, like 1 unit, and dimers are 2 units. But when you get a polymer, these polymers are often millions of units long, and you can't digest them. So it's unlikely they could do any harm to you unless you happen to choke on something. All right. Now, I need a couple volunteers. Okay, if you've got your hand up and you can get to the aisle, I need like 4 people to come up here. All right. This is good. Okay, that's good. Okay, now I need a volunteer who's strong. You want to do this? Okay. All right, we're going to do a little experiment here. Can you guys help me just move the liquid nitrogen? No, you don't want to do that. Let them do it. It's very cold. Okay, so what I want you to do is come over here. I'm going to move this around to get here. Okay, and this is the hard part, because you have to hold this heavy bag up. Oh, thank you. Somebody want to hold the microphone so they can hear me? Thank you. Okay, can you hold this like this? So first of all, what is she holding up? A Ziploc bag. What's a Ziploc bag made out of? You got to get plastic. Good. It's actually polyethylene that we've been talking about. Now, each of you is going to get, you can just rest it there for a second. Yeah, it's heavy. Each of you is going to get a weapon, and I don't want anybody to get hurt with this weapon. So what do we do with my weapons? They're there. Thank you. You've done this? Well, then you got to do it so everybody can see you. Okay, so I need you guys to stand back, and I'm going to have you come up one at a time. Take a pencil, take a sharpened pencil. All right, that's good. That's good. Pick one. You want to do this? You get to go first, okay? Can I give you this pencil? That's good. Okay, now I need you to all go over here, okay, so they can see. Can you hold this up? But you can just very gently put that pencil in. Just lift it up so they can see. Now put it in slowly. Just don't pull it out. Go ahead. Perfect. Go ahead. Keep going. Excellent. Okay, that's good. That's fine. Lift it up. Is it leaking? No. Okay. You can put your pencil in. Go slowly. You can go all the way through if you want with the pencil. But you got to make it so they can see you. Well, it's not leaking through with a pencil. There you go. And you can go all the way through. Oops. Yep. Perfect. Okay, lift it up a little so everybody can see. Can you lift it up? Okay, can you guys see that this pencil, they've gone through? Yeah, but put it in slowly, okay, and don't pull it out. Just go ahead. There might be a slight leak. Yeah, go ahead. There we go. Keep going. Perfect. Okay, you want to do it? Go slowly. Don't stab it. Just Yeah, like that way through. Perfect. All right. Thank you. Can you guys all see this? It's not really leaking, and that's because these polymers simply rearrange themselves around the holes. So you can try this at home. Just make sure your parents are okay with it and you do it over the sink, because if you pull out any of these, they will leak. Now, if I can, everybody who's participated, I want to give you a present here. Do we have, there's some on the right there. All right. They're going to give you, there's some that are open. Shoot. I brought along periodic tables. Anybody know what a periodic table is? Good. It's got all the elements. So you're going to get a table that has all the elements. So if you can.
Okay, my brother's gonna come.
Yeah, and if you need one for your brother, you can have another one. So I want to thank these guys for helping. This was great. And why they're going back to the seat, I need to tell you a story about the periodic table. So if you have a periodic table and you look at element 106, it says SG, and SG was an undergraduate who was in our first class of chemistry. I would tell you that Glenn Seaborg sat in here, but it was on the main campus. We built this a few years later. And Glenn Seaborg went on from the university, from UCLA to what I'll call the University of California North. Yeah, we were the University of California South, so Berkeley we can call North. Anyway, we didn't have a PhD program at the time. He went there and he worked on transuranium elements. So he discovered plutonium. It was kept secret during World War II for obvious reasons. He discovered 10 elements. After World War II, it was announced one day he's driving to work and he hears on the radio that he and the guy he worked with, Macmillan, who ran the cyclotron, had shared the Nobel Prize. He was 39 years old. So Glenn Seaborg used to come back to UCLA twice a year. Once because we gave a prize to a professor under the age of 40 in honor of his Nobel Prize at age 39. So the joke is if you got tenure, you're probably going to win the Junior Seaborg Award. So one year I won that. A few years later, they named the element after him. And at the awards ceremony, his son came to me and he's like, Rick, did my father ever give you his element 106 pin? I'm like, no. He said, come with me, Dad. He won the award. Give him the pin. So I had an element 106 pin given to me by Glenn Seaborg. Yeah, so I tell all the undergraduates when I'm teaching chemistry that someday you could be on this periodic table. Why not? All right. So we have many polymers here. Oh, I want to answer a question for you, or ask a question, which is if anybody actually read the abstract. They made me have an abstract. How many polymers are in an average-sized bowling ball? Yeah. You know? So that's an interesting guess. I'll come back to that in a second. So, how many people think there's more than 1 billion polymers in a bowling ball? Well, that would be a good guess. I'm going to go down. Anybody for 1 million polymers? 1,000? 10? 2? 1. So it turns out that there is only one polymer in a bowling ball. Why? Because, of course, there are hundreds of billions of units thrown in. But then what happens is you put in a cross-linking agent. And so with a bowling ball, it's hardened. It's completely cross-linked. So essentially, there's only one polymer. You can't pull it apart. Now, do we have rubber bands to pass out? Okay. We're going to pass out rubber bands. What do you think rubber bands are made out of? Rubber, good. And again, where does rubber come from? The rubber tree. And anybody know where rubber trees are? Do we have them in our backyard? They are in the Amazon. In what country? Where's the Amazon? What continent? Brazil, yes. In what continent is Brazil in? Anybody know the continent where Brazil is? South America, good. Okay. So I've been invited a couple times to Brazil to give lectures. And I visited a lab that worked with the gutta-percha tree, which is the rubber sap. Anybody want to know what the color of natural rubber is? Do you know? That is excellent. It is white. So it's a little off-white. So here is the sap from a gutta percha tree that they gave me when I visited Brazil. So we'll pass this around. Don't open it. Just pass it around. You can take a look. Now, does anybody know so the natives and even Native Americans use the sap from trees to play different kinds of ball. But the problem is you can't make tires out of rubber. Does anybody know why? With natural... Yeah, in fact, so rubber has a thing called creep. And creep in material science is a time-dependent change. So if you had a pure rubber tire and you parked your car, it would take on the shape of the curb. And so you came back the next day, your tire would be flat. So somebody discovered the vulcanization of rubber. Does anybody know who discovered that? You seem to know the parents will know because there's this blimp that flew around. Goodyear. Yes. So Charles Goodyear discovered the vulcanization of rubber. Does anybody know where he did it or how he did it? You know? Oh my. Wow. We're going to have to go for the double jeopardy question pretty soon. So he got that exactly right. So he mixed sulfur into the natural rubber, and he was playing around in his kitchen, and on the stove, when he got it hot enough, the sulfur vulcanized the rubber. At least that's what he called it. What the sulfur does is sulfur is an 8-membered chain, and if you heat it up, it breaks apart into what are called radicals. And those radicals cause the cross-linking of the rubber. And so basically, he turned the rubber into like a bowling ball. And it turns out, depending on how much sulfur you put in, how cross-linked it is and how hard it is. So rubber tires are cross-linked, but they're not completely cross-linked. And what color should rubber tires be on your car? Well, they are black, but what color should they be if they weren't colorized? They should be white. Okay, so why do we make them black? Can you imagine if you had white tires and you drove home from the car dealership, what your tires would look like? Yeah, they'd look disgusting, right? They'd be all matted up. So, what do we do? How do we make tires black? What do we put in them? Any ideas? Food coloring would be good, except the trouble with food coloring is organic chemistry, and organic stuff fades. Like if you take grape juice, you can make a solar cell. We do this for undergraduates. But the solar cell, with time, the light fades the color. We don't paint our house with food coloring because it wouldn't last more than 1 year. We paint it with inorganic chemicals. I'm an inorganic chemist, that's why. Because it lasts a very long time. So what do we use? Do you know what we put to make them black? That is correct. We use carbon in the form of graphite. We put it into the tires and make them black. Okay, now, does anybody have white wall tires? Has anybody heard of white wall tires? Yeah. So what are they? Because the rubber is supposed to be white, fancy cars will have a white stripe around it called white wall tires. The only trouble is you have to keep cleaning it. But some people like that just because it's for historical reasons. All right, so that's pretty good. Let me see what else we have. Does anybody know what these things are? Peanuts. What do we use these? They are wrapping peanuts. What do we?
We use it to put it in boxes with like fragile things to keep it cushioned.
That's exactly right. And what are these made out of? Styrofoam, yes. So styrofoam is polystyrene. You can find it on your list of 7 things. However, there's a new modern thing that is much better than styrofoam because styrofoam won't degrade. But if I take this, and excuse me, I'm going to just get this wet, and I can stick these 2 things together. Yeah, what? So there we go. I just stuck these together. Now, you couldn't do that if this were styrofoam. Does anybody know what this is? Yeah, well, it is a soft version. You know what this is? Well, okay, we're going to come back to those of you who can cook. If you're making a soup and you want it thicker, you're making a sauce, What do you add to make that? Cornstarch. That's exactly what this is. This is cornstarch. So it's a natural polymer. You could eat these. I'm not recommending that. But I'm going to pass these around. And actually, there's a children's toy where you can buy these and get these in different colors. Here they are. And then they do put food coloring in case somebody eats it so they're not toxic. But you can play with these. So let me pass these around. And if anybody wants to get these wet and stick them together, help yourself. But you can play with these. And it would be good. The only reason all of them aren't this is if it were to rain and your package got wet, that'd be a problem. But if you're buying something on Amazon and you need to protect it, it's a great way to protect it. All right. There are other ways to do it. Anybody know what this is? Foam. What kind of foam? Polyurethane foam. Wow. You guys are good. So all your mattresses, your seats in your car, they're all made out of polyurethane foam. And so I've been to one of the plants in Michigan where they make car seats. And they simply take two parts and they throw them together and they do this. If your home isn't well insulated, and a lot of homes in Southern California aren't, you can actually have them come to your house and they'll stick polyurethane foam into your walls or into your attic, and it will turn into really nice insulation. So this says it's an anxiety brick. You can play with this, but we can send this around. Here, catch. There you go. Yeah, it's not going to hurt anybody. So that is polyurethane foam, and we'll do a few experiments in a moment. Let me see if anybody has questions before I continue. Oh, all right. I've been told I better do my next experiment. So what do I have here? A Starbucks cup. And if I look at the bottom, what number am I going to see on a Starbucks cup? What do you see? Can you read that? 5. What is 5? Polypropylene. So this is polypropylene. It could have been number 2, but it is number 5. And I'm going to do an experiment where we're going to make a polymer. So can you grab this? So I'm going to take part A and part B, and I'm going to measure these out very, very carefully because I am a chemist. There, how's that? Looks good, right? And it's important to get this right. So that was A. Here comes B. B's got an extra cap on it, so I don't screw this up too badly. There we go. Okay. And that looks like about an equal amount, right? All right. We measure this very precisely. I got a straw here. So I'm going to mix this up. And while I'm mixing it up, I want you to touch this and tell me what temperature this is at. Can you feel it? What temperature? Pretty normal room temperature. What do you think? Room temperature? A little cold. Okay. Below room temperature. That's good. So you can see we don't have much going on here. We need to add one more ingredient if we can. No, I got this. All right. So let's see what this is. Well, look at that. You know what I just did? I don't know what I did. No, I added some food coloring. Yes. So we added a little blue food coloring, so it's nice and safe. And check out what temperature this is at. You want to touch it? Go ahead. Just still room temperature? Still cold? Okay, you want to touch this? Yeah, pretty good. All right. Why don't you guys touch this? Still room temperatures? All right. So one of the things we know is a chemical reaction, the speed of it, you want to touch this, doubles with every 10-degree rise in temperature. And touch this again. Is it still room temperature? No, it's getting warm, right? Take a look what's going on. You can see that we are making a polyurethane foam milkshake. Go ahead and touch this. Okay. Yeah, it's getting nice and warm. So go ahead. Touch that. And I got to get back to the beginning because I probably added too much. You want to touch this? Yeah, I can take the microphone. Yes. All right. This looks like fun. It's getting very hot, which means the reaction's going crazy. Oh, don't touch the top. It is hot, yes. So now it's doubling with every 10 degrees rise in temperature. So now I got to put it here because I'm making a mess. But you can see, ooh, we're not supposed to touch this stuff, but all right. So what I want to show you, can you grab we're going to pass some of these around and grab that one too. No, not that one. That one and the green one's pretty good. So you can see what this looks like. Yeah. And the way this works is there's a blowing agent in this, and that blowing agent produces carbon dioxide. So again, if we go back to cooking, any of you use baking soda in cooking? Yeah, what does baking soda do? Yeah. Do you know why it helps stuff rise? What kind of gas does it give off? You'll know. Sodium bicarbonate, and what kind of gas comes out of it? Good. It releases carbon dioxide. Yes. So it's this releasing carbon dioxide, it causes this to rise. And that is actually, and there's a cross-linking agent, and this is how we make foam mattresses. So the more cross-linking, the stiffer it is. So if you like foam pillows, a lot of them are pretty open-ended. You'll see the ones going across fairly cross-linked. All right, I think I've been told that I'm supposed to stop. Yeah, but I'm happy to answer more questions. I'm also happy if anybody wants a periodic table, if you come up, I brought enough periodic tables for everybody. Yes. Okay, so thank you for coming. Oh, I got a question here. Yeah, so cellulose is a natural polymer. If you think about it, if you take anything like celery or vegetables like that, it's filled with cellulose. It's long enough chains you can't digest it. So if you eat celery, you get almost no nutritional value. You certainly don't get any calories. In fact, it takes negative calories. So if you're on a diet, it's great to eat things like celery that have lots of cellulose in it. Yeah, go ahead. Cellulose, yes, you can make paper out of cellulose. So if you took something like papyrus, the original paper was made out of that, and it's high in that. We put a lot of fibers into our like dollar bills and stuff, so you can make paper out of that. Anybody else have a question? You don't really want to touch that. It's really sticky. You end up looking like this. But oh, thank you. Part of my job. Anybody else? All right. Well, thank you all for coming. If you want to look at any of these polymers, if anybody wants a periodic table, if you want more things on recycling plastics, you're welcome to. And if you have any samples, eventually just bring them up here. We'll be here and take care of them.